Welcome to our new learning path on battery cell manufacturing. We have put together a series of video clips to share our experience on mitigating fire risk in lithium-ion cell manufacturing. Throughout this series, you will gain insight into challenges of battery fires, learn about risk assessment, and dive deep into process steps and technical implementation examples. Before we get started, just a few words about me. I'm Gerd Hülsen, and I've been working in the fire safety industry for Siemens for over 26 years. Since 2015, I worked to build up the fire safety application engineering at Siemens Smart Infrastructure. Not only at Siemens, but also as a member of the Real Alarm Board and Vice Chair of the Extinguishing Section. I work to reduce risk of fire, especially in new applications. Now I'm excited to share with you what we are doing in this field of fire safety for lithium-ion battery cell manufacturing. Global warming has led to a strong desire for decarbonization of energy supply, resulting in rapidly growing use of renewable energies. This shift presents an engineering challenge in the field of electricity supply. Managing fluctuation supply. In the future, we will see many more applications of lithium-ion battery storage systems near renewable energy sources, primarily to help balance the grid and serve as a reserve or emergency power supplies. Decarbonizing the transportation sector requires electric vehicles. These vehicles and battery energy storage are the main drivers for the high demand for lithium-ion batteries today and in the near future. This explains the rapid expansion of manufacturing capacities. From today until 2030, we expect approximate tripling production capacities for such batteries. Let's talk about the inherent fire risk. I'm pretty sure the most of us are following the increasing number of protection issues associated with lithium batteries over the last years. Battery fires on airplanes, mobile phones catching fire, EV fires, warehouse fires, and finally fires in lithium-ion battery storage. For us, reason enough to start working to understand the problem and develop suitable solutions for this new type of fire hazard. All in all, aiming to the prevention of catastrophic events, including fire and explosions. Li-ion battery applications need an advanced fire protection system. Fire safety is a regulated business, and it's crucial to be aware of both global and local regulations. Our comprehensive portfolio offers solutions that comply with these regulations on both levels. Our fire detection systems provide reliable and fast detection of fire incidents, notifying intervention forces, and initiate controls to prevent further damages. Our notification and evacuation systems ensure fast and controlled evacuation of people via voice alarming, provide information for intervention forces, and include alarm notifications via sounders, beacons, and lighting. Our suppression and extinguishing system suppress fires to prevent further spreading and extinguishing fires using natural agents. Lastly, our danger management and digital service offer alarm monitoring, incidents and service management, and involve workflow efficiency for engineering and commissioning. With these solutions, we ensure comprehensive fire safety that meet both global and local standards. In our holistic approach to gigafactory safety, we recognized that fire safety solutions must address both the building and the machinery to ensure sustainable and safe battery cell production. For building safety, separating fire safety critical process steps such as the formation process from other production areas is crucial. Fire-resistant walls recommended to enclose these areas. For example, following the guideline of the German Model Building Code and VDI 3564, structural fire resistance up to 120 minutes, as referenced in standards like NFPA 855, provides a helpful benchmark alongside recommended separation distances outlined in FM Global Datasheet 5-33. Fire suppression and extinguishing systems, such as sprinklers and gas extinguishing systems, should integrate with fire detection system to ensure rapid response. Furthermore, limiting hazardous materials and incorporating off-gas detection systems contribute to robust process safety, helping to prevent explosive atmosphere. For machinery safety, backup measures like temperature-controlled water suppression system can mitigate risk if gas systems fail. Even these should be the last resort. Automating processes like removing damaged cells with stacker cranes minimize risk to personnel, enhancing operative fire safety. Together, these strategies underline our commitment to aligning safety with efficient and sustainability. So, modern lithium-ion batteries come in three common designs: cylindric, prismatic, and pouch cells, each with its own advantage and disadvantage that impact energy density and preferred use cases. Cylindrical cells are round and enclosed in a robust metal casing. With a common size like 18650 or 21700, they offer high energy density, excellent durability, and good thermal management, making them cost-efficient to produce. These cells are commonly used in electrical vehicles like Tesla, power tools, and e-bikes. However, their form factor can make them slightly heavier and less flexible in size. Pouch cells have no rich casing and are encased in a flexible foil, usually made of aluminium laminate. This design offers the highest energy density, especially in terms of weight. They are lightweight and adapted to various shapes, making them ideal for smartphones, tablets, and high-end electrical vehicles. The downside is their reduced mechanical stability, requiring additional protective measures. Prismatic cells are rectangular and housed in a sturdy metal or plastic casing, allowing for space-saving integration, especially in applications with limited space. Prismatic cells are widely used in European and Asian electric vehicles, as well as in large-scale energy storage systems. Their drawback includes the more complex manufacturing process. When comparing energy density, pouch cells rank highest in terms of weight, followed by cylindric and prismatic cells. In terms of volume, pouch and prismatic cells perform similarly well, while cylindrical cells lag slightly behind. The choice of design depends on the specific requirements of the application. For robust and cost-efficient applications, cylindrical cells are ideal. Prismatic cells excel in space-saving integration, while pouch cells are the best choice when weight and flexibility are critical. Each design has its unique strengths and is suited to different applications. Now, let's take a look at how lithium battery fires start and how they can be controlled. Typically, there's a kind of abuse, like a short circuit, in one of the cells, due to aging, a mechanical defect, or overload or overcharging. This causes the cell to warm up at temperatures above 80 degrees Celsius. The highly flammable electrolyte vapor starts to boil and escape from the cell. This temperature goes on increasing until the separator falls. This leads to a catastrophic temperature increase in the battery and consequent explosion of the combustible electrolyte gases. The development of a thermal runaway can be shown using a circle, starting far left with the green segment, the battery abuse, leading in some cases to smoldering, always followed by off-gassing, followed by separator breakdown and thermal runaway, leading to off-gas explosion and finally an open fire. When the first battery go into thermal runaway, it heat adjacent battery, starting a domino effect, which with thermal runaway spreading from cell to the next and to the next. Obviously, this is important to stop the development of that chain reaction. What would you assume is the last point at which this chain reaction should be stopped? Yes, the process must be stopped before thermal runaway of the first battery is completed. The intervention must be made at the latest immediately after the off-gassing event. After the off-gas event phase, we lose the battle against thermal runaway. The following slide shows the progression of a thermal runaway and explains measures to prevent catastrophic events. The key to the successful minimizing the impact is detecting of an off-gas event before the separator of the first battery cell collapses. If this is achieved, nitrogen can be introduced into the battery's surrounding before the separator collapse to prevent the ignition of the released gases, mainly hydrogen and carbon monoxide. This prevents both gas explosions or deflagrations and open fires. Additionally, the ignition of the highly flammable liquid electrolyte is prevented, reducing the total amount of released energy. This, in turn, prevents the propagation of thermal runaways from cell to cell or from battery module to battery module, depending on the battery module design. This briefly describes our VDS certified protection concept for managing lithium-ion battery fires. With the right fire protection strategy, you can protect life, assets, environment, and ensure business continuity. We have proven that lithium-ion battery fires, especially in scenarios where off-gassing can be detected early, can be effectively controlled through timely intervention to prevent catastrophic consequences. Our approach ensures that lithium-ion batteries become a manageable risk. Thank you for your interest in today's session. I look forward to seeing you again next time.